All right, in this video, we will be going over section 7.4. Section 7.4 is about introduction to convergence tests. Okay, basically, we will be talking about certain tests that we can use to determine the convergence or the divergence of a given sequence. Okay, and we will be going over a bunch of examples in these sections. All right, first, I want to go over this theorem, so-called divergence test. Here is what the statement of the theorem tells us. If the sequence AK does not converge to 0, then the series K goes from 1 to infinity, AK diverges. Okay, this theorem helps us to determine when a series could diverge. That's why you call this the divergence test. Okay. Again, if the sequence AK does not converge to 0, then the corresponding series K goes from 1 to a sigma K goes from 1 to an AK diverges. Okay, let's give a quick proof of this theorem. How do we prove this theorem? First of all, let's assume that this sequence AK does not converge to 0. Okay, that means limit as K goes to infinity, AK is not equal to 0. That's what we mean by this sequence does not converge to 0. If it does not converge to 0, this limit cannot be equal to 0. So I will assume that this is not equal to 0. Okay. Then what do we have to show? We have to show that this series diverges. If I assume this condition, that means if I assume this, I have to show that this series diverges. Okay. What I'm going to do is, for a contradiction, I'm going to assume that this converges. And I'm going to come up with a contradiction at the end. Okay. So for a contradiction, assume that this series converges. We want to show that it diverges, of course, but I assume that it converges, and then I'm going to come up with a contradiction. Okay. All right. If this series converges, what can you say about the partial sum? First of all, if this series converges, that means there exists. That is, there exists some L, some positive number, some real number L, such that limit as K goes to infinity, the series K goes from, pardon me, yeah, this is just the series. Sigma K goes from 1 to infinity, AK is equal to L. That's what we mean by this series converges, right? If this converges, there has to be some real number L, some nice real number, so that this series is equal to, the summation is equal to that L. Okay. Now, I'm going to consider the sequence of partial sums. Okay. We know that if this series converges, the sequence of partial sum also should converge to L, right? So, this implies Sn, the sequence of partial sums, converges to L as n goes to infinity. Okay. If you want, you could use the indexing letter to be k as well. Then this will become k. Okay. So let's use n. Sn, the sequence of partial sum, also converges to L as n goes to L if this series converges to L. Okay. So here, let me recall you the sequence of partial sums. Sn means sigma K goes from 1 to not all the way up to infinity, just up to n. AK. That's what we mean by sequence of partial sums n, or n partial sum. Okay. So we know that Sn approaches to L as n goes to infinity. Okay. Now let's make another observation, that is Sn minus 1 is equal to A. Let me write the expanded version first. Sn minus 1 is equal to Sn is sigma K goes from 1 to n AK, and then minus Sn minus 1 is K goes from 1 to n minus 1 AK. What is this difference? This difference is clearly going to be an, right? That's because here you take the sum of the first n terms, and here you take the sum of the first n minus 1 terms. That means this difference has to be equal to an, nth term, right? Now, what I'm going to do is I'm going to take the limit of both sides of this equation. We know that Sn minus 1 is equal to an. So this limit statement has to be true. Limit as n goes to infinity, Sn minus 1 should be equal to limit as n goes to infinity an. Okay. Now, take the limit of the left-hand side. What is the limit? This limit as n goes to infinity. I can, of course, send the limit, apply the limit to each individual term. As limit n goes to infinity, Sn is equal to, from this statement, that is L, right? Because we know that Sn approaches to L as n goes to infinity. So this limit is L. What is this limit? What happens to this as n goes to infinity? Again, as n goes to infinity, even if you have a minus 1 here, n minus 1, this whole thing also goes to infinity. So this term also approaches to L as n goes to infinity. So the left-hand side becomes L minus L. The right-hand side is limit as n goes to infinity ak, which is equal to 0. Why is it 0? Because L minus L is 0. Okay. So that means, but remember, our starting hypothesis was limit as k goes to infinity, ak is not equal to 0. But at the end of the day, it turns out that limit as n approaches to infinity, this is an, of course, an is equal to 0. This is a contradiction, right? Because this is right opposite of what we assumed at the beginning. Okay, so this is a contradiction. That means our assumption is wrong. We assume that this converges, right? It does not converge. Okay, so that means this is a contradiction. This is a contradiction. That is, I will use IE for that is, the original sequence, the series diverges. K is equal to 1 to infinity. AK diverges. Our assumption was wrong. Our assumption was converges, but it gave us a contradiction. So the original series diverges. Okay, this is the divergence test. Now let's go over an example to understand how to apply the divergence test. Okay, here is the example that I want to work on. Determine whether the series k goes from 1 to infinity, k over k plus 1 whole thing to the power k converges or diverges. Okay, so if we are going to apply the divergence test, then we will be showing that the series diverges, right? So let's show that this given series diverges using the divergence test. Okay, to apply the divergence test, what do we have to, if you want to show that this diverges, what do we have to show? First of all, let me identify my k. I'll take this to be my k. This quantity to be my ak, okay? Not k, ak. The general term, right? So then, to show that this diverges, using the divergence test, what do we have to show? First of all, let's read the statement of the divergence test. If the sequence AK does not converge to 0, then the series diverges. So all we have to do is the sequence AK does not converge to 0. If we can show that the sequence AK does not converge to 0, then we are done. We can conclude that the series diverges using the divergence test. Okay, that's what I'm going to do here. I'm going to show that the sequence AK does not converge. And that means I have to show that, I'm going to show that limit as n goes to infinity, an is not equal to 0. That's what we mean by this sequence. That's what we mean by the sequence AK does not converge to 0. Okay, we need to show that this limit as n goes to infinity, an is not equal to 0. Okay. All right. How do we show that this limit does? Maybe we will write k here. Okay, instead of n, let me write k. We need to show that limit as k goes to infinity, ak is not equal to 0. Well, let's deal with our ak. We know that our ak, first of all, we need to calculate limit as k goes to infinity, ak. My ak is, of course, k over k plus 1 whole thing to the power k, right? This is equal to limit as k goes to infinity, as k goes to infinity. I'm going to rewrite the terms, okay, inside. I can write this inside piece, this piece as 1 over 1 plus 1 over k. And then I have this power as it is. Okay. So how did I do this one? All what I did was I divided both top and bottom of this fraction by k. If you divide your top by k, just you get 1, right? And if you divide your bottom by k, this k divided by k is 1. You have 1 here. And this 1 divided by k is 1 over k. That's how I got this expression. Okay. Now I'm ready to take the limit. Okay. Before I take the limit, I'll take the power of both top and bottom separately because I have the power k here. So I will apply the power to the top and bottom separately. So this is going to be equal to limit as k approaches to infinity, 1 to the power k. 1 to the power k is just 1, right? Plus 1 over k to the power k. I just applied the k power to the top and bottom separately. All right. Now we have a quotient, right? If you have a quotient, you can take the limit of the top and the limit of the bottom separately. What is the limit of the top? This is a constant, right? 1 is just a constant. So limit of the top is just 1. What is the limit of the bottom? Limit as k approaches to infinity, 1 plus 1 over k to the power k. What is that limit? Is that something familiar to you? This limit? Well, in calculus 1, we discussed this limit. The value of this limit is actually e. Okay. If you don't remember that, please review your calculus 1 notes. It's in the chapter review of calculus 1. Okay. The chapter 1 review in calculus 1. This limit is going to be, limit of this expression is going to be e. As you can see, this is not equal to 0, right? E is a number, which is like 2 point something, right? 2.7 something. That is not equal to 0. That means the limit as k goes to infinity, ak, is not equal to 0. If it is not equal to 0, by divergence test, this series should diverge, right? As you can see from this statement, if the sequence does not converge to 0, then the series diverges, okay? So by divergence test, this series, k goes from 1 to infinity, k over k plus 1 to the power k diverges. Okay, this completes that example. Let's move on. All right, next, another extremely important, extremely useful theorem, which is called the integral test. Okay, this is theorem 7.28. Let's see what integral test tells us. Okay, if ax is a function that is continuous, positive, and decreasing on the interval 1, infinity, and ak is the sequence defined by ak is equal to a of k for every k, every positive integer k, then the series sigma k goes from 1 to infinity ak and this integral 1 to infinity ax dx either both converge or both diverge. What does this theorem actually tell us? First of all, we should have a function a of x. Okay, that function has to be a continuous, positive, decreasing. All these 3 criteria should be satisfied. Okay, otherwise you cannot apply the integral test. Okay, this is something that you need to be keep in your mind. Okay, some students are applying these tests without checking the criteria. Then they come up with the wrong answer. Okay, so remember, if you want to go with the integral test, the function has to be continuous, positive, and decreasing on this interval 1 comma infinity. And your sequence AK, you should be able to obtain the sequence AK by plugging the K in your function. AK is equal to A of K. A of K means you plug in the integer K in your function AX. That will give you the K term of the sequence. Okay, sequence AK. And then what the test tells you is that this series and this integral either both converge or both diverge. What that tells you is that if this integral converges, then the series also converges. If this integral diverges, then the series also diverges. That's what it simply tells you. Okay, so we can apply this theorem to determine whether a series is convergent or series is divergent. Okay, if this integral is convergent, if this integral converges, then the series also converges. If the integral diverges, then the series also diverges. Okay, that's the bottom line. All right, now I'm going to quickly give you the geometric idea of the proof of this theorem. Okay, let me show you the give you the idea only for one case. Let's assume that this integral diverges. Okay, then we need to be able to show that corresponding series also diverges, right? If we assume that this integral diverges, what does that mean in terms of geometry? Well, for that, to explain that, let me draw the graph of the function a of x. Okay, if I draw the graph of the function a of x, it looks like this, right? It's a positive function. We are given that it's a continuous positive decreasing function. So it has to be a function like this, right? Going down, it should be positive and it should be decreasing. Okay, so if we have a function like this, what is this quantity? Let's assume that the integral diverges. Okay, assume that the integral 1 to infinity a of x dx diverges. Then we will show that the series also diverges. Then we will show that the corresponding series k goes from 1 to infinity ak also diverges. How do you show that? Well, it's the geometry. This is a geometric proof. Okay, this is not a formal proof. Here is the graph. First of all, what is this integral? This integral is nothing but the area under the curve on the interval 1 to infinity, right? Because the integral bounds are from 1 to infinity. So the area under the curve on the interval 1 to infinity is the integral. This integral is the area under the curve on the interval 1 to infinity. That means this area. This area, right? You take all the way up to infinity. Okay. All right. Now, notice that I have a partition here, right? 1, 2, 3, 4, 5, so on and so forth. And then in each interval, I'm going to construct a rectangle. The way I construct the rectangle is on this interval, I'm going to find the maximum value of the function. Clearly, on this interval, the maximum value of the function is this value, right? Right here. With that height, I'm going to complete a rectangle. This is my first rectangle. Similarly, on the second interval, I'm going to take the maximum height of the function. That is, of course, obviously this height. And then with that height, I'm going to construct a rectangle. So on and so forth. I construct rectangles in each interval. Notice that by the geometry of this picture, the sum of the areas of the rectangles is clearly bigger than the area under the curve, right? Because each rectangle is an over approximation for the area under the curve in each interval. Okay, this area is smaller than the area of the rectangle. Okay, so if I take the sum of the rectangles, area of the rectangles, then that sum should be bigger than the area under the curve. But what is the sum of the rectangles, areas of the rectangles here? What is the area of this rectangle? That is width times height, right? Notice that width is always 1. The difference between 2 and 1 is 1. This length is 1. So 1 times this height, right? This height is just A1. This height is just A2. This height is just A3. So that means the area of this rectangle is A1, area of this rectangle is A2, area of this rectangle is A3, so on and so forth. That means this summation will give you the areas of all those rectangles, right? All those rectangles. Okay. As you can see, summation of all those rectangles should be greater than this integral because this integral is the area under the curve. Clearly, that area is smaller than the area, sum of the areas of the rectangle. So that means we have this inequality, right? Now we are done. We are almost done. We assume that this is integral diverges, right? We assume that this integral diverges. Clearly, if this diverges, this has to diverge. Why is that? Because the series, the sum of the series is bigger than this integral. If this is a bigger quantity, this smaller quantity diverges, then the bigger quantity should also diverge because they are all positive quantities. Okay. All right. I mean, the bigger series should diverge because this smaller thing diverge. Okay, diverges. All right. Similarly, we can show that if this integral converges, then this series also converges. Okay, the idea is similar. You can use this geometry of this diagram to show that. Okay. All right. That is about the integral test. Let's move on. Notice that here, when I say this diverges, this goes to infinity. Okay, that's what I mean by this diverges. So this goes to infinity. This integral is equal to infinity. That means this sum also should be infinity. Infinity means it diverges. Okay, infinity is not a real number. All right. Now let me walk you through an example. Here is the example that I want to go over. Basically, application of the integral test here for this example to determine the convergence or divergence of this given series. Okay, determine whether the series k goes from 1 to infinity, k over e to the power k squared converges or diverges by applying appropriate convergence test. Okay, clearly I'm going to apply here the integral test. Okay. Well, as always, let me identify this as my AK. This is the general term AK. AK is equal to k over e to the power k squared. Okay. If I want to apply the integral test, then I have to identify my function AK, right? Pardon me, AX. What is my function AX going to be in this case? Pause the video for a second and think about it. What is my function AK going to be in this case? Remember, if I am planning to apply the integral test, it has to be a continuous positive decreasing function. Okay. Well, how do you find AK in this case? It's very easy. Given the example, if you know AK, then AX is immediate. Your AX is going to be, I'm going to take my AX to be, I'm going to replace my k by x, e to the power x squared. This is my AX is going to be, okay, e to the power. Let me write this a little bit clearly. K over e to the power, pardon me, x over e to the power x squared. That's my AX. Okay. Notice that it's not hard to justify that this AX is a decreasing function. How do you show that this is a decreasing function? Take the derivative and show that the derivative is negative. If the derivative is negative, show that. I will leave that as an exercise. Show that AX is decreasing. Okay, basically show that A prime of X is negative. It's a very simple calculation. You can easily see that your A prime of X is less than 0. Okay, so that means this function is decreasing. Notice that it's clearly a continuous function on the interval 1, infinity. It's a continuous function on the interval 1, infinity. Remember, it has to be a continuous positive decreasing function. So it's a continuous function clearly, and it is decreasing because a prime of x is negative, and clearly it is also positive. Okay, for x bigger than on this interval, as long as x is in this interval, this function is positive. All right, now all the criteria for the integral test are satisfied, so we can go ahead with the integral test. Okay. So basically, we are going to show that this diverges, this converges using the integral test. To apply the integral test, I'm going to have to calculate this integral, right? I need this integral 1 to infinity ax dx. What is this? 1 to infinity ax. Ax is x divided by e to the power x squared dx. This is nothing but 1 to infinity x times e to the power minus x squared dx. I brought this term to the top by making the power negative. Okay. So how do we do this integral? Okay. So it's not hard to see that if you use a substitution, u is equal to x squared, you can find this integral. I'm not going to show you the calculation. Actually, if you do the calculation, you should get, this is going to be, first of all, notice that this is an improper integral. You have infinity as the upper bound. So let me write this integral as limit as b goes to infinity, integral from 1 to b x times e to the minus x squared dx. This is equal to limit b goes to infinity. If you integrate this function and apply the limits 1 to b, you should get this expression minus 1/2 times e to the power minus x squared, and of course now you need to plug in the bounds 1 to b. Okay, lower bound is 1, upper bound is b. Okay, so the integral of this function is exactly what you have inside here. You can verify that by differentiating this quantity. Okay, so I'm not going to go to integration because you did all these things in calculus 2. Okay, now if I plug in these limits, you will get, this is equal to limit b goes to infinity minus 1/2 times e to the power minus b plus 1/2 e to the power minus 1. This is equal to 1 over 1/2 times e to the power minus 1. Okay, that's because as e goes to infinity, this quantity goes to 0. Because we know that this as b goes to infinity, this becomes e to the power minus infinity. E to the power minus infinity approaches to as b approaches to infinity, this whole thing approaches to 0. Okay. All right. As you can see, this integral converges, right? It's a finite number. This is a nice finite number, less than infinity. Okay. Now, by the integral test, our series also converges. First of all, let me write our integral 1 to infinity ax dx converges, because this is a finite number. Okay. Thus, the original series k goes from 1 to n, k over e to the power k squared also converges. Also converges. By what? By integral test. I'll write IT for integral test. Okay. All right. That completes that example. Let's move on. Okay. Next, we have another very important theorem, which is called the convergence and divergence of P series. Okay. So basically, what we mean by the P series is a series of this form. Okay. sigma k goes from 1 to infinity, 1 over k to the power p, where this p is any real number. A series of this form is called a p series. Depending on this value of p, we can determine whether this series converges or diverges. Okay, here is the criteria. If your p is bigger than 1, then the p series, this is what we call the p series, okay, converges. If this p is bigger than 1, then the p series converges. And if p is equal to 1, this series is given a special name. When p is equal to 1, that name is the harmonic series. Okay, if you plug in p is equal to 1 here, this is the series you get, right? That is called the harmonic series, and that series diverges. This is extremely important series when you do analysis. Okay, if you go to a higher math course, and if you take a course like analysis course, mathematical analysis course, this sequence, you will see this sequence often. Okay, so this is called the harmonic series, and the harmonic series diverges. And then if p less than 1, if this value of p is less than 1, then this series diverges. Okay, all right, very helpful theorem. Okay, and the proof of this theorem is a straightforward application of the integral test, and I will not be going over the proof of this theorem. Okay, it's very so straightforward. All right, next I want to go over this definition. Go over this definition. Definition 7.30. The remainder of a convergent series. Okay, if the series k, sigma k goes from 1 to infinity, is a convergent series with some L. With some L means this is equal to L. Okay, let me quickly write it here. Sum is L means this series is equal to L. If this series is a convergent series with some L, then we may approximate L with the n partial sum. N partial sum means the summation of the series from k goes from 1 to n. 1 to all the way up to only n. Okay. All right, what does this mean? If this series convergent, if the series converges to L, then it says that we can approximate L. L means the summation of this series with the n partial sum Sn. What does that mean? First of all, what do you mean by this series converges to L? That means the sequence of partial sums should converge to L, right? So in other words, if sigma k goes from 1 k goes from 1 to infinity, ak is equal to L, then the sequence of partial sum Sn approaches to L as n approaches to infinity. By definition, right? Sequence of partial sums should also approach the same L as n goes to infinity. What does that tell you? That means when n is getting larger and larger, your Sn is getting closer and closer to L. That means if you choose your n large, your Sn should be an approximation for your L. That's what we mean by Sn approaches to L as n goes to infinity. As n goes to infinity, your Sn is approaching to L. That means if you choose your n to be very large, your Sn has to be very close to L. Okay, so Sn is approximately equal to L. This is the symbol to say that approximately equal. Okay, Sn is approximately equal to L when n is large. Very simple definition. And then what is the next the other part? The nth remainder is defined by Rn is equal to L minus Sn. That's how we define the nth remainder, okay, which is denoted by Rn. Rn is nothing but L minus Sn. Notice that L is the summation of the full series. K goes from 1 to infinity, ak, and Sn is the summation only up to n. Okay, so what would you get if you take this difference? It should be summation k goes from n plus 1 to infinity ak, right? Because this here you have the full series, summation k goes from 1 to infinity, but this is the summation, Sn is the summation k goes from 1 to n ak. Okay, if you take off that part, you get the tail part of the series, right? Tail part is k goes from n plus 1 to infinity ak. This is what we call the remainder, nth remainder, and it is defined by this equation. Okay, here is the idea. So if you have this original sequence, k goes from 1 to infinity ak, that is the summation of all the terms, then clearly this is the nth partial sum, which is denoted by Sn, and here is the tail part. This tail part is what we call the nth remainder. This is what we call the nth remainder. Nth remainder is sigma k goes from n plus 1 to infinity ak. Okay, it is denoted by Rn. It is nothing but L minus Sn. Okay, this whole thing is L. If you take off Sn from that, then you get the tail part. All right, let's move on. Next, we have this theorem, which states how to approximate the remainder of a series that converges by integral test. Okay. All right, here is what the theorem tells us. If a function a is continuous, positive, and decreasing, same criteria that we were using in the integral test. Okay, function ax has to be continuous, positive, and decreasing. And if the improper integral 1 to infinity ax dx converges, then the nth remainder Rn, which was denoted by Rn, for the series k goes from 1 to infinity ak, is bounded by this quantity. Bounded by these numbers. Okay, Rn is the nth remainder. Okay, that is nothing but L minus Sn. What is L again? L is the summation of the full series. Sigma k goes from 1 to infinity ak is what we call L. Okay, of course, Rn is L minus Sn. Sn is the nth partial sum. Okay, this is the definition that we saw earlier. Okay, so this Rn is always between 0. 0 is a lower bound, and this is an upper bound for the nth remainder. What is the upper bound? That is this integration. Integral from n to infinity ax dx. That's an upper bound. Further, if you take bn to be this upper bound, whatever the upper bound you have here, if we take this to be bn, if I define that to be bn, then the summation of your original series, that is the original series, that has to be between Sn and Sn plus bn. Okay, so this original summation, or this is nothing but L. Okay, this L has to be between Sn and Sn plus bn. All right, let's look at an example now. Here is the example that I want to look at. Use the third term S3 in the sequence of partial sums to approximate the sum of the series. This is the series given to us, and use theorem 7.31 to find a bound on the remainder. Okay, remainder for this particular n. N is 3 in this case. Notice that n is 3 in this case. For that number, you need to find the nth remainder. In this case, that is the third remainder, because n is equal to 3. All right, first of all, let's find an approximation. Okay, from this from the previous definition 7.30, we know that our partial sum will be an approximation for the original series, sum of the original series, if you choose your n large, right? In that case, they are asking us to choose your n to be 3. You might be wondering, 3 is not large, so would that be an approximation? Well, in this case, for this particular series, yes, even though this 3 is not that large, still this S3, this partial sum, is going to be a very good approximation. You will see that in a second. Okay, so let's find S3. We are going to approximate the sum of this original series by this partial sum S3. S3 is equal to, basically you take the summation of the first three terms, right? 1 over e to the power 1 squared plus 1 over e to the power 2 squared plus 1 over e to the power 3 squared. That's it, right? So what is that going to be? Well, you can use a calculator to find this one. This is going to be, if you calculate this using a calculator, this is 3 squared, okay? Using a calculator, of course, it's not going to be an exact answer, it's an approximation because we have to round to certain decimal places. Let's round it to 6 decimal places. 0.404881. That's the approximate value for this summation. All right, now the conclusion is that from definition 7.30, this partial sum is an approximation to the sum of the original series. Okay, so we could write summation k goes from 1 to infinity, k over e k squared is approximately equal to 0.404881. Okay, so we approximated the sum of the original series by a partial sum. Okay, next we are asked to use theorem 7.31 to find a bound on the remainder. Okay, that means we need to find this bound. We know that the remainder is already bounded below by 0. Remainder has to be bounded below by 0. Okay, first of all, notice that that's something I mentioned in the previous example. Remember, in the previous example, we were dealing with this function, right? We saw that this was a decreasing function. Okay, so notice that here the function that we are working with, if you take this to be ax to be x divided by e to the power x squared, this is a decreasing function. We saw that in the previous example. Okay, so that's why we can apply this theorem. Remember, a has to be a continuous positive decreasing function. We saw that this is a continuous positive decreasing function in the previous example. Okay, that's something I should have noted at the beginning. All right, anyway, now we have that. Now we need to find a bound for the nth remainder. In this case, nth remainder means third remainder, right? Because n is equal to 3 in this case. Okay, so let's find a bound for third remainder. Okay, third remainder. Let me write bound. Bound for third remainder. So it has to be greater than or equal to R3. R3 has to be greater than or equal to 0 and less than or equal to whatever we have here. That should be this integral. Integral 3 to infinity ax dx. Okay, notice that your ax is, of course, in this case, this function. That is going to be 3 to infinity ax dx. That is 3 to infinity x over e to the power x squared dx. Okay, I'm not going to show the integration here, the computation, because I showed that in the previous example. So if you compute this, you will get 0.000062. That's going to be your answer. That means your third remainder, R3 is between 0 and 0.000062. Okay, that's the bound. This is an upper bound for the third remainder, and this is a lower bound. Okay, we are done with the example, but we can do one additional thing here. Remember, we have a second part for this theorem, right? Theorem 7.31. We found an upper bound and a lower bound, and the second part also tells you that the sum of the original series is between Sn and Sn plus Bn. Remember, Bn is nothing but this upper bound, whatever the upper bound you have here. Okay, Bn is this integral. Okay, but in this case, notice that our n is 3. Okay, this becomes 3. So by the second part, let me write further. Further, we have S3 less than or equal to the summation of the original series 1 to infinity k over e to the k squared, that is less than or equal to S3 plus B3. B3 is nothing but this integral. This is your B3. Remember, your Bn was this integral, that is this upper bound. That is exactly this one. Okay. So since we have the value for all of these components, we can write an inequality here. This summation of this original series, k goes from 1 to infinity, k divided by e to the power k squared has to be greater than or equal to S3. Pardon me, let me put 3 here. Okay, S3, we found the value of S3, which is 0.404881. 881, and then this should be less than 0.404881 plus B3. Your B3 is this one. This is this number. Okay, that is 0.000062. What does that tell you? Let me quickly add a page. This tells you that the sum of your original series, k goes from 1 to infinity, k over e to the k squared, this sum is between these two numbers. What are the two numbers? This is 0.404881 and the other number is 0.404943. This tells you that this actual sum, the original sum of the series, is between these two numbers. Okay, that means, see, as you can see, these two numbers are equal for 3 decimal places, right? Because this is 404. Here also you have 404. Okay, so this 0.404 is the accurate sum for this series for 3 decimal places. Okay, that sum is accurate for 3 decimal places. All right, let's move on. Here is the next example that I want to go over. Find all non-negative values of P for which this given series converge. Okay, we need to find all non-negative values of P. P is the power here. Okay. So how do we find those P values so that this series converges? Well, we are going to apply the integral test. Okay, to apply the integral test, the first thing is that we need to identify a function AX. Okay, in this case, I told you how to identify the function AX. You basically replace your K by X, right? If you replace, this is your AK, by the way. In your AK, if you replace your K by X, then you get your function AX. Okay. Notice that this function is a decreasing positive continuous function on this interval. Okay. Clearly, it is positive on this interval, right? On this interval, whenever X is a positive number, this whole thing is positive. Okay. And it is also continuous because this function is continuous and the bottom function is continuous. So the quotient of continuous functions is continuous because this is non-zero. This is always positive. Okay. And also it's a decreasing function. You can show that it is decreasing by showing that your A prime of X is negative. This is an exercise for you. Okay. Show this. All right. Now, notice that all the hypotheses for integral test are satisfied. Okay. So if you visit back our integral test, it is the integral test. If ax is a function that is continuous, positive, and decreasing on 1, infinity, and if ak is the sequence defined by ak is equal to a of k for all positive integers, then both this series and this integral either both converge or both diverge. Okay, that was the integral test. All right, now we can apply the integral test because all the criteria are satisfied. For that, to determine the convergence of this series, I'm going to compute the integral. What integral do I need? I need to compute this integral. 1 to infinity ax dx. That is integral from 1 to infinity. My ax is, of course, x over 1 plus x squared to the power p dx. Okay, we need to compute this integral. Of course, you can easily calculate this using u substitution. If you use u is equal to 1 plus x squared, that should give you the integral, an easy integral that you can compute. All right, so this will be equal to, if you use the substitution, it will become 1/2 times integral from 2 to infinity du over u to the power p. Okay. Okay. Now by calculus 2, actually it's theorem 5.21. 5.21 in calculus 2, we know that this integral converges if p is greater than 1, and this diverges if p is between 0 and 1. 2 to infinity du over u squared converges if p is greater than 1 and diverges if p is between 0 and 1. Okay, that is coming from calculus 2. Okay, what does that tell you? Note that this series does whatever this integral does, right? That's what the integral test tells you. Okay, that means we know that this integral converges if p greater than 1. That means this series also converges if p greater than 1. We know that this series, integral diverges when p is between 0 and 1. That means this series also diverges when p is between 0 and 1. Okay, so let's write it. Let me add a page here. By integral test, IT means integral test. Okay, integral test, sigma k goes from 1 to infinity k over 1 plus k squared to the power p converges if p greater than 1. That's because the corresponding integral converges if p bigger than 1. Okay, and let me write, and k goes from 1 to infinity k over 1 plus k squared to the power p diverges if p is between 0 and 1. Okay. All right, that completes that example, and that also completes this section 7.4. I'll stop there and I'll see you next time.